Hi guys, last class we are discussed about for the overall heat transfer coefficient for the cylindrical as well as the inner based on inner radius and based on the outer radius. Now I will continue that one. We can have to go for the analysis of heat exchanger. So there are there are two methods are there for the application of analyzing the heat exchanger. They are first one called as logarithmic mean temperature difference called as LMTD method, and second one called as effectiveness called as NTU method. So within that first one we go for the LMTD method. LMTD means logarithmic mean temperature difference. So what called as a logarithmic mean temperature difference is nothing but called as the thermal analysis of heat exchanger depends upon the variables like inlet and outlet temperatures of the fluids and overall heat transfer coefficient, and also total surface area of the heat exchanger and the heat transfer rate. So these are the factor we have to consider the analysis of the heat exchanger. So within that first one, the temperature difference between the hot and cold fluids is given by called as delta T. Delta T is nothing but called as TH minus TC, where TH is called as temperature of the hot fluid and this was called as temperature of the cold fluid. TC is the temperature of the cold fluid. So if you're taking a difference between the hot fluid and the cold fluid, you get the temperature difference. So as we already discussed about the types of the heat exchanger, the delta T is not a same for all the position. For example, let us consider the parallel flow and the counter flow heat exchanger. Look at here. One, let us consider this is called as hot fluid and this is called as cold fluid. So within that, observe that in this type of heat exchanger, the hot fluid and cold fluid, the temperature difference initially, that means this point and this point, initially is difference should be some value, but when you go for the next position, if you're taking that off of the position are exit temperature, that temperature is not same. So that means that the temperature difference between the hot fluid and cold fluid will be depends upon the position. We can take if you take this position, temperature difference should be different. If you're taking this position, temperature difference should be different. So at that time, we have to take the logarithmic average value of the hot and cold fluid temperatures. So that time we called as, so look at it, I'll mention here, delta T is varying with position along the heat exchanger, along the length of the heat exchanger. When the length of the heat exchanger goes to vary from one position to another position, the delta T is also varying with position. That is, change in temperature is not same for all the position. Hence, for that one, we have to take the mean temperature, mean value. So mean value. So hence the rate of heat transfer is given by, as per the overall heat transfer coefficient concept, U is equal to U is the overall heat transfer coefficient, A is the surface area of the heat exchanger, and delta T mean. Delta T is the temperature difference between the hot and cold fluid, but we have to take the mean value. So because of the temperature difference will be vary with position. So that's why along the length of the heat exchanger. So that's why I have to take the mean value. So where delta T is the mean temperature difference across the heat exchanger. So now for the heat exchanger, the mean temperature difference will be in the form of logarithmic relation. So hence it is referred as a logarithmic mean temperature difference called as LMTD. So now before going to analysis of the heat exchanger, some assumptions should be made. So that means using the LMTD method, some assumptions should be made. So within that, the first assumptions are the overall heat transfer coefficient is uniform. That is, U is the uniform throughout the heat exchanger. And second one, the specific heat and mass flow rate of the both the fluids are constant, is not get varied. Specific heat and as well as the mass flow rate should be constant for the hot and cold fluid. The potential and kinetic energy across changes are negligible. So that is, change in kinetic energy and potential goes to neglected. And that one, the heat exchanger takes place only between the two fluids. Not more than 3 fluids. We have to take the only 2 fluids only. We have to take into account. So the temperature of the both the fluids are constant are given across section. Suppose if you're taking that any position along the length of the heat exchanger, the temperature difference, temperature of the fluids are constant. So these are the assumptions have to made before the analysis of the heat exchanger. So now we have to go for the first one, we called as analysis of the parallel flow heat exchanger. We already discussed about the types of heat exchanger. So within that, very important one is called as parallel and counterflow heat exchanger is the very important one. So within that, we have to analyze the parallel flow heat exchanger using the LMTD method. So now this is the schematic diagram of the parallel flow. That means for the parallel flow, both the fluids, hot fluid as well as the cold fluid, will be flows in the same direction. So now look at it. This is the temperature and length of the heat exchanger diagram. That is temperature profile diagram. This is called as temperature profile diagram. In y-axis, we have to take the temperature. At the same time, x-axis, you have to take the length of the heat exchanger. Look at it. Initially, the hot fluid having a higher temperature, cold fluid having a lower temperature. Hence, the temperature difference, initially starting point, it should be more. Delta T, that is called as temperature difference, should be more. So that's why we have to take an THI. Within that, this is called as THI is the called as hot fluid temperature at inlet, and TCI is the cold fluid temperature at inlet. At the same time, TH0 is the hot fluid temperature at outlet, and TC0 is the temperature of cold fluid at outlet. So now when observe that when compared to the inlet to the outlet, the temperature difference goes to lesser because of the hot fluid gain the heat energy. Hot fluid loses the heat energy, at the same time cold fluid gain the heat energy. So hence the temperature to taken in y-axis, for the cold fluid, temperature is gradually increases from inlet to outlet. At the same time, the hot fluid will be loses the heat energy, and hence temperature will be decreasing takes place. So where theta 1 is the temperature difference at inlet between the hot and cold fluid, and we call as theta 2 is the temperature difference at the outlet between the hot and cold fluid. So now let us consider within the overall length of the heat exchanger. This is the length of the heat exchanger. Let us consider a small element of area dA. Let us consider small elemental area. So this is the small elemental area we called as dA. So within that dA, where theta is the temperature difference for the small element. For the small element, the theta is the temperature difference. So where along with when compared to the for a small elemental area, this distance we called as change in temperature of the hot fluid, and this is called as dTc is the small change in temperature of the cold fluid. So now let us consider a parallel flow heat exchange as shown in figure. So already introduced that notations have to use, and some more notations have to use in that one, where CPH and CPC are the specific heat of the hot and cold fluid. CPH is the specific heat of the hot fluid and CPC is the specific heat of the cold fluid. At the same time, MH and MC are the mass flow rate of hot fluid as well as the mass flow rate of the cold fluid, where A is called as surface area of the heat exchanger. So now we have to take that from the diagram. Observe that theta 1 is nothing but called as THI minus TC1, temperature difference, and theta 2 is called as TH0 minus TC0. So this is the equation. I'll write it. Theta 1 is equal to Thi minus Tci. Theta 2 is equal to Th0 minus Tc0. So now, according to, and another assumption I have to made, sorry, I forget to tell, the heat exchange between the two fluids only. So neglect the heat losses to the surrounding. So that means what are the amount of heat energy lost by the hot fluid? That is equal to amount of heat gained by the cold fluid. So that is heat transfer to the surroundings. To the surroundings goes to neglected. So according to that energy balance equation, that is heat lost by the hot fluid is equal to heat gained by the cold fluid. So within that, let us consider Q, that is a heat energy. Q is equal to heat transfer rate can be expressed in terms of mH into Cph into Thi minus Th0. This is for the hot fluid as well as this is for the cold fluid, that is mc Cpc Tc0 minus Tci. So, and this one we can rearrange that one. Q is equal to Ch, and that means Ch is nothing but called as product of mH into Cph. So that is called as Ch, or the heat capacity rate for the hot fluid. Ch is the heat capacity rate for the hot fluid, as well as the Cc is the heat capacity rate for the cold fluid. So Cc is the called as mc into Cpc. I'll write that this is called equation number 1. So now within that I'll give the expression here, and now let us consider a small elemental of thickness dx and area dA as shown in figure. So the rate of heat transfer for the hot fluid. Now we have to take that individually. For the hot fluid we called as dq. dq is the small rate of heat transfer rate. So is equal to, look at it, minus mh into Cph into dTh. Actually you can ask a question, sir, why you are not taking the minus sign here, why you are taking the minus sign here? Because of, look at it, the temperature difference always we have to take it into the outlet to the minus inlet. So actually this will become actually like that, minus of mh Cph and Th0 minus Thi. So when compared to the inlet, outlet having a lesser value, hence this product will become negative side. So in order to avoid that one, I'll transfer that negative sign into the inside. So this is become mh into Cph into, that is Thi minus Th0. Got it right? But look at it. When you're writing for the cold fluid, look at here, outlet minus inlet. Got it right? So here we have to take the delta Th. Delta T is change in temperature. Change in temperature having a negative value. This product having a negative value. So that's why I'll write that negative. So mH into Cph into dTh is equal to, so that we called as mH into Cph we called as Ch, heat capacity rate into dTh. So using that equation we taken the dTh as a thing, that is equal to minus dq by dh. Because of here I have to identify the LMTD, logarithmic mean temperature difference. So that's why we have to take in the temperature terms separately. So now let us consider this is called equation number 2. So similarly for the cold fluid, dq is equal to mc Cpc into dTc. So this is a heat gain. So that's why it is positive. So hence that means this product will be become a positive only. So hence that is equal to Cc into dTc. So the dTc is equal to dq by Cc. So this is called equation number 2. This is called equation number 3. So for the small elemental area, we can write that dq is equal to, that is u into dA, because of small elemental area having area of dA, into delta T. Look at here, I'll write that equation here. The rate of heat transfer equation is UAS into delta T. UAS into delta T, that means called as, here also I'll write it that U into dA into Th minus Tc. So that is equal to U dA into theta. Theta is nothing but called as hot temperature difference between the hot and cold fluid. So hence therefore theta is equal to Th minus Tc. So this is called equation number 4. So now if your small elemental area, change in temperature dt, this also dTh and this is equal to dTc. So from equation from 2 and 3, these two equation can be replaced by dH in terms of minus dq by ch, and at the same time dtc is equal to, we can write that dq by cc. In the next step I'll write that one. So now look at it. So now this is the equation. I'll write it here like that as it is. So dq is equal to, here dq is the common for the both the sides and dq is the taken common out. So what are the remaining things? 1 by ch plus 1 by cc. So now from equation number 4 we can write that, that is equation number 4 tells that dq is equal to u into dA into theta. So hence dq can be replaced by minus u dA into theta into 1 by ch plus 1 by cc. So that means theta term temperature difference we are keep it separately, that is this will transfer to this side, d theta divided by theta is equal to u dA into 1 by ch plus 1 by cc. So this is equal to plus, right. So now if you want to take the temperatures, we have to integrate this equation. So along the length between the inlet to outlet. So integration of above equation with respect to 1 to 2, as well as u is a constant, overall heat transfer coefficient, and this is also constant, mass flow rate is and specific heat constant, then automatically ch and cc are the constant capacities, but area goes to change. This is small elemental area, but we want to take the entire overall area. So hence 0 to AS called as entire surface area of 1 into dA. So if you integrating that 1 by x into dx, we call as ln x, like that, ln theta of 1 to 2 minus u into 1 by ch plus 1 by cc into 1 into differentiation of a 0 to AS. So hence this will become ln of theta 2, having apply the limit, upper limit minus lower limit, ln theta 2 minus ln theta 1 is equal to minus u AS, upper limit minus 0. So that is UAS into 1 by ch plus 1 by cc. So at the same time we go for the ln of, this is in the form of log m minus log n. So this is log m by n. So that is ln of theta 2 by theta 1 is equal to minus US into 1 by ch plus 1 by cc. Keep it as it is. So now from equation number 1, we know that from equation number 1, where is the equation number 1? We can check it once. So look at it, this is the equation number 1. From this equation number 1, we can write that Thi minus Th naught is equal to Q by Ch. So that one I will write it here. From equation number 1, Thi minus Th naught is equal to Q by Ch. At the same time, Tc naught minus Tci is equal to Q by Cc. So hence we have to identify the 1 by Ch. So 1 by Ch is equal to Thi minus Th naught divided by Q, and 1 by Cc is equal to Tc naught minus Tci divided by Q. Now substitute that value of 1 by Ch, 1 by Cc into this equation. We're getting that ln of theta 2 divided by theta 1 is equal to UAS into Thi minus Th naught divided by Q and Tc naught minus Tci divided by Q. I'll substitute here. So next step, within that Q is a common. Q is the common, take it out. If Q is a common, taken out, you're getting that ln of theta 2 divided by theta 1 is equal to minus UAS Q into, look at it, within that I'll grouping Thi minus Th naught minus of Tc naught minus Tci. So within that minus UAS, keep it as it is, we are rearranging this equation. We're getting that Thi minus of Tci and minus as it is Th naught minus Tc naught. So I'll group it. So where according to that diagram, Thi minus Tci we call as theta 1. That is equal as Thi minus Tci is equal to theta 1. At the same time, Th naught Tc naught equal as theta 2, and here also Th naught minus theta 2 equal as theta 2. So hence this minus sign is transferring to this side, because this will become ln of theta 2 divided by theta 1 is equal to UASQ theta 1 minus theta 2. If you are transferring to that side, this will become ln theta 1 minus ln theta 2, hence ln of theta 1 theta 2. So is equal to UAS into Q theta 1 minus theta 2. If you get getting confused, I'll write it here. I'll change how to change that one. Look at it. When you go, that is ln of theta 2 divided by theta 1 can written as ln theta 2 minus ln theta 1. So if you are minus, this is the actual expression. So that is ln theta 2 minus ln theta 1 is equal to minus UA by Q something. If you transfer into this side, this will become minus ln of theta 2 plus ln of theta 1. So hence this is become ln of theta 1 minus ln of theta 2. So therefore this is the form of ln of theta 1 divided by theta 2. So that one I'll write it directly. Minus ln of theta 2 divided by theta 1 become ln of theta 1 by theta 2. So now that is this is the equation UAS divided Q and theta 1 minus theta 2. So here Q, we want Q in the form of UAS into, that will transfer into, this will transfer into this side. So theta 1 minus theta 2 ln of theta 2 divided by theta 1. So the above equation in the form of, this equation will be form of Q is equal to UA into delta T mean. Hence UA as it is, and this is equal as delta T mean, where delta T mean is equal to theta 1 minus theta 2 divided by ln of theta 1 by theta 2. So this is the equation is called as logarithmic mean temperature difference. We called as LMTD for the parallel flow heat exchanger. So now we go for the next one. We called as for the counter flow heat exchanger. So when compared to the parallel flow and counter flow heat exchanger, only one difference is there. Method and derivation should be same. Only one thing will be difference. Look at it. Within that, this is called as hot fluid and this is a cold fluid. We can write it. Hot fluid and cold fluid will be flows in opposite direction. Hence, look at it. In this one, length of the heat exchanger, along the length of the heat exchanger, the temperature difference, look at it, within that, the hot fluid loses the heat energy, so hence temperature from inlet to outlet goes to decreases from year to year. Look at that R mark. R mark is the very important for the parallel flow and counter flow heat exchanger. This is the counter flow. This is opposite direction. This is the opposite direction will be flows. So hence at the same time, cold fluid will be inlet here and outlet here. So hence the temperature difference is also again increases. So temperature go for the inlet to outlet goes to increases. So now I'll give the comparison between the parallel flow as well as the counter flow heat exchanger. So look at it. This is the THI as it is, TH0 as it is, write it. So even though curve will become the same thing, but cold fluid will be flows in opposite direction. So hence instead of like that, we have to write like that. Look at it. This is the TCI. This is the TC0. This is the TC0. This is the TCI. This is the for parallel flow. This